Welcome to MEI Modelling with Algorithms. We're on the topic of Linear Programming 1, Introduction, and this is video 1.1, Formulation of Linear Programming Problems. Now, linear programming is an extremely powerful technique, and it can be used to solve all sorts of problems in all sorts of different contexts, maybe economic problems, other sorts of practical problems. Anything where we've got constraints on, for example, time, materials, numbers of workers, things like that, lend themselves very well to being tackled using linear programming. Typically in real problems there'll be a number of what we call constraints, and when we get to the algebra these will be written as linear inequalities. And there's normally something that we want to either maximize or minimize. So for example, we might want to minimize time or cost, maximize profit, something like that. And whether we're maximizing or minimizing, it's called optimization. So we're just making something the best that we want. And in order to define the thing that we want to maximize or minimize, we create what's called the objective function. And again, we will write that algebraically. Now, all we're going to be doing in this video, to be honest, is showing you how to formulate a wordy problem into the algebraic form that a linear programming problem should really begin in. And then in the later videos we'll go through the various processes we can use to actually solve the problem. But actually often sometimes the most challenging part in solving a linear programming problem is translating a wordy description of the practical real life situation into the formal algebra. Now typically we have several variables involved. These will relate to things involved in the practical problem. So if we're dealing with something in a chocolate factory, we might be assigning a variable for the different amounts of different types of chocolates which are produced. And the aim of linear programming is to find the values of the different variables that we are free to pick from that will give us the best result, the ones that will optimize our objective function. And in later videos, when we get onto solving linear programming problems, we're going to be dealing with problems involving two variables and doing that using a graphical method. So here's an example of a sort of worded description of a practical problem that is the starting point for linear programming. I'll invite you to pause your video for a moment to read through that. Don't even try to solve it by any means. Just read through it and try and take on board what the problem is asking. So, quite a complicated question, this, especially if you've not met anything like this before. Now, as I say, in this video we're just going to look at how we can translate this into algebra. So what we're really looking to do is to create variables to describe the things that we are able to sort of choose in order to try and find the best choice, and also think about how we can express the information which is there in terms of the constraints. So for example, each machine is available for only 1 hour, and the objective function, which is the profit in this case, because we're told we're trying to maximize the profit. How can we express that thing algebraically in terms of our variables? So when you're choosing your variables, you need to think about what are the things which you're actually getting to choose between. And the key to that is to read this final part, the actual question itself. How many of each type of box are we going to make? So for each type of box we'll have a variable which will stand for the number of boxes of that type that we're going to make. So why don't we start with the variable x? We've got type A boxes, so we'll say that we're going to make x boxes of type A. And then it'll be sensible after that to say we'll make y boxes of type B. Now that we've defined our variables, let's turn our attention to the constraints, and the first constraint I'm going to talk about is the one involving the folding machine. So we can see here type A boxes require 4 seconds on the folding machine, type B boxes require 2 seconds on the folding machine, and the machine is available for a maximum of 1 hour. So what we need to do is express that information using an inequality. So what is the total amount of time that we're going to be using the folding machine for? Well, if all I did was make one box of type A, and that's all I did with that machine, that would take 4 seconds. So if x is 1, then the time it would take would be 4. If I make 2 boxes, then I'd be doing that twice, it would take 8. So the time that we're spending making type A boxes is just 4 times the number of boxes that we make, so it's 4x. So the first thing I'm going to write down in my inequality is 4x. There we go, 4x. So that's the time making type A boxes on the folding machine. And then type B boxes, they require 2 seconds on the folding machine, so by the same argument, that's going to add a time of 2y for the time that is spent using the folding machine to make type B boxes. And we know that the total time available on that machine is 1 hour, so the amount of time that we spend has to be less than or equal to 1 hour. Now let's be careful with units here. These numbers are in seconds, and this unit is obviously 1 hour. Quick calculation tells us that 1 hour is 3,600 seconds. Now you might spot that we've got a common factor of 2 here, so it's probably sensible to simplify this by dividing through by 2. And then the other constraint, of course, is going to come from the stapling machine. Type A, 6 seconds per box, type B, 7 seconds per box. So by exactly the same reasoning as before, that means that we'll have 6x, that's the time making type A boxes on the stapling machine, plus 7y, which is the time making type B boxes on the stapling machine. Again, we've got a maximum of 1 hour on that machine, so that must be less than or equal to 3,600, and there's no common factors there to divide through. There are also 2 more constraints which always have to be there in linear programming problems. X is a number of things. Clearly it's not going to ever make sense for x to be negative, so for completeness we say that x is greater than or equal to 0 and y is greater than or equal to 0. And a similar thing to say as well, because these are countable numbers of objects, we're not going to be making half a box ever. We should also say that x and y have to be integers. And when we come to look at solving linear programming problems, we'll see what difference that makes. And the final thing, which we've not said anything about yet, is the objective function. Now in this case we're talking about the profit, so we might give the objective function the variable name p, and we need to think about what that is in terms of x and y. Well, we're told that we make 40 pence profit on type A, so that would be 40x, obviously using units of pence here, and 30 pence on type B, so that will be 30y. And that's the thing that we're going to try to maximize. So just to sort of summarize that in a more tidy way now, the linear programming formulation for that is that we're going to maximize P, which is 40x plus 30y, subject to these constraints. So we have a constraint on the use of the 2 machines. We have the then natural constraints on these objects, so numbers of objects, so obviously have to be non-negative integers, and just for completeness, just to make it clear what each of these things stands for in the context of the real problem, because once we do go about solving this, we'll need to interpret our solution in order to actually get something useful out of it that we could apply in that real life context. Now, as linear programming problems go, that was a relatively straightforward one to formulate. There are all sorts of different types of constraints and all sorts of different ways of phrasing them, so the more experience you get with this sort of thing, the more of these you'll meet, and you'll get more of an idea of how to do it. We're just going to look at a couple of more difficult constraints to interpret and see if we can make sense of them. You might want to pause your video here and look at these two and see if you can have a go at it yourself first. Now, with the first one, actually, a mistake I see a lot of people making when you have something like this is that you the sentence almost leads you to try to associate the number 2 with the dark chocolates, and it's very tempting there to think that you're going to be writing down a 2y and a single x. But if you think about it carefully, what it's saying is that the number of dark chocolates, so that's just y, has to be at least twice the number of milk chocolates. So that actually means that y must be at least 2x. And so we'll write that in the following way. We'll say that y is greater than or equal to 2x. And then for this second question, it says that the dark chocolates must be less than 40% of the total number of chocolates. So again, dark chocolates, okay, so that's y, less than, now 40%, well that's the number 0.4 multiplied by something, and that something is the total number of chocolates, and of course the total number of chocolates is x plus y. Now, at this stage, if you want to, you could leave it like that, but as you'll see in later videos, we might want to plot this thing graphically, so it might be an idea to simplify this so that we don't have y appearing on both sides, for example. So from there, we'll go up to the top right and continue where we've got a bit of space. We can say that y is less than 0.4x plus 0.4y. I can now take that 0.4y over here by subtraction, leaving 0.6y less than 0.4x. And it might be nice to get rid of these decimals and write it in terms of integers, so I could multiply by 10 to get 6y is less than 4x, and then divide by 2 to get 3y is less than 2x. So that concludes video 1.1. We've seen how to formulate linear programming problems now. In the next video 1.2, we're going to see a graphical solution using the vertex method.